So the last speaker of this morning's program is Professor Sara Seager. Sara is the class of 1941 professor of planetary sciences and professor of physics. Her work is the search for planets that have signs of life, and does this through computer models of exoplanets, atmospheres, interiors, and biosignatures. Today, she will talk about, is there life out there? Sara?
Okay, good afternoon, everybody. Thanks for all of your patience. And I'm here to tell you about planets beyond our solar system. It may seem at first like a real juxtaposition with all the other talks, which are about here on Earth, and most are practically oriented. But I want you to know there's such a huge overlap in terms of sort of the science and applied physics. With microbial life, we try to understand what might exist in extreme environments elsewhere. With the greenhouse gases, you know, it's the same techniques we use to model Earth's atmosphere, and for remote sensing techniques to study Earth with Earth-orbiting satellites that we're going to be using to study planets and their atmospheres far away. So I love to start with this picture, which is a photograph of a dark sky. Because what we'd like, and it's, our eyes can't see quite this well. This is like a time exposure. But our thought always is that someday, hopefully soon, we'll be able to go to a dark sky and to take our nieces and nephews and children and grandchildren and even great-grandchildren and to point to a star and say, that star has a planet like Earth. That star has signs of life by way of gases in its atmosphere. Now, I take these thoughts very seriously, but then until I see Neil Papalardo, he and some of my other MIT alum friends, every time I see them, they say, no, they want me to find signs of life beyond Earth in their own lifetime. So I'm here today to try to tell that to you. And before I get started, for those of you that aren't following exoplanets in the news, it's such a growing thing. It's really surprising and very remarkable. What I call it is the awakening that started really, to me, in 2009 when myself and 30 other astrobiologists went to the Vatican. We were invited to stay inside the Vatican. The Pope and others wanted to know what was going on exoplanets in case anytime soon we were going to be finding planets and signs of life. They wanted to think for themselves what that effect would have on them. Fast forward to many things happened in between, of course, but last December, when I was invited to testify before Congress to the House on Space, Science, and Technology on the status for the search for Earths and for life beyond Earth. So people are getting excited at all levels to try to understand what this will mean for us. And I just needed to give you that brief intro, sort of in contrast to the very practically oriented talks we heard, that we're here to use applied physics and space engineering to try to answer one of the most fundamental questions we as humans have ever come up with. So back to the stars in the sky. Just to remind all of us, every star in the sky is a sun. And if our sun has planets, we naturally expect all the other stars to have planets also. And they do. We think that in our own Milky Way galaxy, which has 100 billion stars, statistically speaking, astronomers have found that every single star has at least one planet. But what is so fascinating, and one of the points I want to convey to you, is that really none of them are anything like our own solar system. Just to remind you about our solar system, here's a schematic showing you the sun in the middle, and Mercury, Venus, Earth, Mars, and Jupiter. The other planets, Saturn, Uranus, and Neptune, don't fit on here on scale. And basically, it's just sort of to remind you of that. And we have found thousands of exoplanets we know about. Here's a cartoon diagram showing you them all made in a pattern here. And this is showing you some results, a subset of results from the Kepler Space Telescope. And it's showing you the size of the object relates to the size of the planet, and the orbits and how fast they go around relate to the planet-star separation. Okay. I had a bit of trouble with this microphone. If you want to know the truth, it's because, like for women's clothes, they just don't make them right for microphones. So here you go. Here's the, I'll have to face this way. You guys won't see me, but here's the animation. I mean, look at that. There's so many schematics of so many planetary systems out there. It's a selection effect. We haven't been able to find one like our solar system, but I'm trying to capture for you the just ultimate diversity. So many planets, so many systems out there. And we have found some crazy systems, such as one that has 6 planets, and all those planets, 5 of those 6 planets, orbit interior to what would be Mercury's orbit. If you were paying attention to the news last week, you would have heard about this new planet found. This is an artist's conception. We don't have any planets that we see in this level of detail, Kepler 10c. And what is so awesome about this planet is its mass is 17 Earth masses. Just as we had, in theory and in observation, gotten used to the idea that for a purely rocky planet, its maximum mass would be about 10 Earth masses or less, we just found this ginormous rock. It's our latest thing that we're excited about. And there's so many examples, I wouldn't have time to go through them here, but astronomers have found planets that are so close to the star, their time to go around the star is less than a day, and they're heated so much by the star to the point that their surfaces are hot enough to melt rock. There's other planets that orbit 2 stars. We call them circumbinary planets. That would be like us having 2 suns. One sun would rise and set, and the other one would be rising and setting on a different scale. But if there's one thing that you could remember about the recent news about exoplanets, that's this, going to be described by this plot. And this is the thing that I'd like you to go home and tell your friends and family. And that is about the occurrence rate of planets. This is a bar chart, and it's showing you on the y-axis the, let's see if I can, fraction of stars with planets. This number has changed, but the bar, I just want you to really look at the size of these relative histograms. This is planet size relative to Earth. 1 Earth size here, up to 20 Earth radii and 11 Earth radii. This cartoon is showing you Earth compared to Neptune and Jupiter. Now, what you can see from this plot here, lots of planets here, small planets, and very few, relatively in comparison, larger planets. But all we had been taught from planet formation was that when a planet starts to form, it grows rapidly until a point when it has a runaway growth process. So a planet like Jupiter, we thought would be extremely common. The planet keeps growing until it's able to have a runaway effect where it sucks in all of the material in its feeding zone and rapidly gets big. What we've actually found is that small planets, that is planets between 1 and, say, 3 times the size of Earth, are far more common, 10 times more common than Jupiter-sized planets. And it's kind of baffling because we only had our one solar system as an example, and people made detailed theories about it. And it's basically back to the drawing board for planet formation. But why it's so exciting, really, is because small planets are common. They're everywhere. And it's really up to us now to figure out how we're going to find those small planets around the nearest stars so that we can study them and look at their atmospheres for signs of life. So what I get asked most often is, people want to know, do we know of any planets that are right for life? Have we found any planets now that we think could have life on them, even if we can't find that life quite yet? And we always revert to this green region here. It's called the Goldilocks zone, or the habitable zone. Rocky planets with thin atmospheres are heated from their star. And so we need to find planets that are a distance from the star so that they're heated to be not too hot, not too cold, but just right for life as we know it. And people always want to know, do we know of any now? And for those of you that do follow the news, you'll know that we've found them supposedly again and again and again. But in fact, we don't really know yet. We have actually, there's this website that's really fun to look at, Current Potentially Habitable Exoplanets. And just based on some very loose constraints, again, we have no images of exoplanets like this. These are just artist conceptions. But based on the planet's size or mass and distance from the star, people like to guess whether its surface could have liquid water, which we think is a requirement for all life. So it's pretty cool to me that although with these we have no idea whether they really are habitable, the fact that astronomers can legitimately come up with a dozen planets we think are what we call possibly having the right surface temperature is the tip of the iceberg. We know that the small planets are very common. We're already starting to find those that could be potentially habitable. So everything is looking great for us. The challenge now is that finding planets has become somewhat standard, but being able to look at their atmospheres to assess their greenhouse effect and the surface temperature and look for gases that might be produced by life is a real challenge. And so we need to move to other ways to be able to other sophisticated space telescopes to find it. So here's the good news. There's sort of mixed news that we have 2 strategies of how we're going to go forward, how we're going to find planets, and how we're going to find ones whose atmospheres we can look at. The basic picture is that here on Earth, our atmosphere is filled with gases, and most of the gases in the atmosphere, although they're naturally occurring, are produced by life. And in particular, the one that always gets mentioned in the terms of the search for life beyond Earth is oxygen. Oxygen fills our atmosphere to 20% by volume. But without plants and photosynthetic bacteria that produce oxygen, we would have basically no oxygen in our atmosphere. And we're hoping that there's an alien civilization like us, not too far away, looking back at us. And if they see oxygen in our atmosphere, they'll be thinking hard about why it's there. It's such a reactive gas, it shouldn't be present in the atmosphere under almost all circumstances we can think of. So we have two plans. This decade, our plan is to look as soon as possible to find the best candidates to look for signs of life around them. It's more likely we have to wait till the future and do a very more complicated option. And now for the second half of my talk, I'll talk about each of those in turn. The first one, we call it transiting planets. And this is how most of today's exoplanets have been found. You can watch this movie. The top shows you a picture of a star. We don't spatially resolve any stars other than our sun like this. What we see as astronomers is this bottom plot. And this is going to show you the measuring, the brightness, as a function of time. And if nothing's going on and it's a relatively quiet or well-behaved star, every time you take an image of it, you just get the same brightness. And for some special cases where the planet and star are perfectly aligned, the planet, by chance, goes in front of the star as seen from the telescope. Can you see the planet here? It's so tiny. It's supposed to represent Earth's size compared to our sun. Earth is very small. And you see that drop in brightness, which is because of the planet-to-size area ratio. And so you see there's this tiny drop in brightness. And NASA's Kepler Space Telescope, which took data for about 4 years and is starting up again, they looked at 150,000 stars and took the same image every 6 seconds and binned it into 1-minute or 30-minute bins to downlink a whole chunk of data to Earth every quarter of a year. And looking for that little tiny drop in brightness. Other things can make it too. But on the whole, that's how most planets are found today. There's many techniques to find them. And so I'm really pleased to tell you that the next big thing that's going to happen for exoplanets is TESS, Transiting Exoplanet Survey Satellite. And that's an MIT-led mission by George Ricker in our Kavli Space Science Center. And it's a NASA mission, and there's other partners involved also. And what TESS is it's essentially 4 very glorified telephoto lenses, very specially made from scratch to not have any blurring effects at the edges, vignetting, or not to have any weird color things going on at a sensitive level. And they have ginormous baffles to block out light from the Earth and Moon. And what TESS is going to do is an all-sky survey. It's going to look at either 500,000 or a few million stars, depending how much data we can downlink to Earth. And we're going to look for the so-called transiting planets around small stars, actually. TESS has the capability to look for small planets around very small stars. And we hope to take that pool of planets found by TESS and to use a new space telescope, which is used to be called the Next Generation Hubble Space Telescope. It's called the James Webb Space Telescope, and we'll look at the atmospheres for signs of life. So actually, TESS is supposed to launch in 2017, the James Webb Telescope in 2018. So within a decade, we're going to survey the small stars around us and have a shot, if any planets are rocky and have signs of life, to find life there. Now, I'm not here to sell it or anything, although people always ask me, what are the chances we're going to find life there? And we have to be really lucky in this case. Every one of these small stars, we know that about half of them have a rocky planet in the so-called Goldilocks zone. But we need all of those planets to be findable. We need them all to have life on them, and half of those with life to generate gases that could percolate and survive in the atmosphere for extended periods of time. So this would be like winning the lottery many times to find it. So we have the capability to find it, but we have to just get really lucky that it exists around one of the nearest candidates and we'll find it. So we're all excited about this. This is the way to go. It's sometimes likened to the person dropping their keys but looking under the streetlight where it's easiest to find. It's what we have accessible to us. So we're going to do it, but it's our nearest term shot at it. And we're going to learn a lot of other things also, but here I'm just directing my talk on the search for life beyond Earth. So what we're doing in parallel, this is going to be happening. We're all working hard here at MIT. But our second thing is investing in the future. It's like any investment portfolio. You want to have something that delivers now, something that delivers in the immediate term, and then you have your much longer term investment, high risk, high payoff. And so that's where I spend an increasing fraction of my time in that blue box, the true Earths orbiting the sun-like stars. These transiting planets are so great. Nature was bountiful. We could study them in a lot of detail. But ultimately, we want to be able to see Earths that are not having any special alignment. We'd like to be able to block out a star directly. We call it direct imaging, to block out the star and to see a planet directly. And the technique that we have in mind that people have been working on for quite some time is to literally put a large screen in space to block out the starlight. Now, the thing is that our Earth is so, as we heard from the last talks, it seems so big. There's much to work on in every little region on Earth and all the big problems we have here. But in the cosmic sense, our Earth is actually so small. It's so small and so faint. Here's just an image of a star. And no matter how many planets are there, the point to convey is that stars are so bright compared to planets. Our own sun is 10 billion times brighter than our Earth. So if we want to be able to block out the starlight to see a planet directly, like our Earth, we have to block out that starlight to 1 part in 10 billion. And I ask you to think for a minute at whatever you do, whatever you work on. Did you ever have to go to 10 decimal places? It's a real problem here. But we have really no other choice if we want to do this. So I have just one slide that kind of relates to physics, and then I'll tell you about the concept. But this concept I'm going to discuss, we call it the star shade. And it literally is putting a giant screen up in space to block out the starlight. Now, if we were to put a circular screen up on the left, or if we used a circular let's say we had the circular screen, we'd get that pattern on the right. I think some of you will remember this from physics class. We call it the airy ring pattern. If a star is a point source, it acts like a particle and a wave, but the waves will actually diffract around the edges of the big circular screen. And instead of seeing a point, you would see these rings. And it's analogous to dropping a pebble in a pond. You get ripples. It's a wave. And that first ripple is so big, right? It's so bright. It's 100,000 times brighter than the planet we would be looking for. So what optical physicists or astronomers have done over the last long time, accelerated in the recent decade or so, was to have a new pattern. What if your screen in space is the shape of that star? You'd get the pattern on the right with that very dark hole. And it's like, that would be like dropping a pebble in a pond. And instead of getting the ripples, all of a sudden, all around that pebble, it's so perfectly smooth to 1 part in 10 billion. And all the ripples are happening out on the edge. It's the wrong way to describe it, but it makes sense to say that it's like pushing all those ripples out to the edge. So a lot of math has gone on, and we're still arguing now about the actual best shape. But that's essentially the idea, to put a large screen in space. And I actually just have notes on this slide for anyone who knows a little more and wanted to read some of the details. But because of ray optics, you end up having a screen that's about tens of meters in diameter. And it has to cast a shadow on the telescope and fly tens of thousands of kilometers away from the telescope. That's how hard the problem is. But you're all MIT. You know that we go after hard problems. And we solve them, and we make it work. And so right now, I'm actually chairing a NASA group that's trying to fold all of this together into a way that actually can be done, that would be starting 5 years from now. So I'm going to explain this concept a little bit further with this animation. And it shows you a star shade and a telescope launching together. They would have launched together. This would be after launch. The star shade petals would unfurl from a stowed position. And this truss would expand with the petals snapping into place. These petals have to be manufactured to be like 150 micron in precision. And like I said, that star shade would have to fly far from the telescope to block out light so you could see planets directly. So what's interesting is petal prototypes have been made. Yesterday, I was at a meeting, and I saw this really cool series of photos from people at Northrop Grumman who've gone to the desert to do subscale testing at the 1% level. And to scale it all properly, they're 3 kilometers away. The telescope and star shade are separated by kilometers. And they have taken images, and they're trying to replicate this 1 part in 10 to the 10 contrast will they get eventually. So the star shade has a lot of technology development going on. Here's from Northrop Grumman last summer. You can see the petals, just like in the animation. These are real prototype petals at 2/3 scale, mechanical, 1-to-1 optical, passively unfurling from their stowed position. And what you see here is a truss, which is actually used. It's left over from developing large radio deployables that go to space. So there's real heritage involved in this project. Now you'll see that second stage of petal deployment with the truss expanding, and the petals are going to snap into place. I always get asked, why are there peoples in this time-lapse movie? It's not to demonstrate that the truss can expand automatically, rather to show that repeated deployments put the petals in the same place relative to each other for the tolerances that will be required to actually block out the starlight to the relative precision. So I hope that you learned something new here. And sometimes exoplanets and the star shade are what people like to call the Cooper effect. It's like if someone points out a Mini Cooper car and you haven't really seen one before, all of a sudden you start to see them wherever you look. And it's really phenomenal. It's the Cooper effect. And so we were so excited the other day when we found on YouTube this song by some random group decided to put a song in their cover. They call it the Star Shade. So you hadn't heard of the Star Shade before today, but I'm pretty sure that you'll remember it now. So to finish off, I just want to say that our Earth is just so tiny in the whole cosmos. This is a real photograph of Earth taken by the Voyager 1 spacecraft at 4 billion miles away. And to the rest of the universe, we are just another exoplanet. So it's really hard sometimes to get around your head all the problems and challenges we face on Earth, in contrast with the vastness of the cosmos. But I just wanted to leave you with that thought that all of the hard work we're doing all across MIT, it all is very interdisciplinary and does indeed end up spilling over into the search for life beyond Earth. Thank you.